today, early from Oregon, and he will be telling us about strongly invertible knots, Khovanov homotopy, and localization.
Thanks, Buland, and thanks very much for coming, everybody. I'm excited to be here. I think it's my first time in the seminar, and excited to tell you about some joint work with Sucharit Sarkar from a couple years ago about Khovanov homology and knots. So this is supposed to be a symplectic seminar. The work is not exactly symplectic, but it's symplectic adjacent. So I'll make a number of connections with symplectic geometry and with related results in symplectic geometry. And the results are sort of inspired, or at least partly inspired by work in symplectic geometry. The talk runs a little bit short, I think, so it'll be a nice, relaxed pace and lots of time for questions. But if you have questions during the talk, please absolutely feel free to interrupt and ask. There's plenty of time. I was going to just sort of use as a cover slide, but maybe, oh, no, two more things. One is it can be a little bit annoying having the slides disappear as soon as I change the slides. So what you're seeing vanishes. So there's a version of the slides available already as a PDF online. I put a link in the chat. So if you want a copy of the slides, you can sort of see the future. The link's also there. Great. And then I thought before I would change the slide, maybe I would use the picture on the cover is, and it's sort of to illustrate what at least tell you what a strongly invertible knot is. So if you take this knot, so this is a S1 inside S3. I'm going to write, by the way. The first slide is pre-printed, but everything else I'm going to write. So the pace will be controlled by my writing speed. So if you take this S1 and S3, there's an axis here, so that when you rotate by pi around the axis, it takes the knot to itself. That's what the pictures from the movie are indicating. And the axis intersects the knot in 2 points. So it intersects it at those 2 points. It's called strongly invertible because if you orient the knot, then when you do this rotation by pi, that reverses the orientation. So this is one of there's sort of 5-ish classical symmetries of knots in 3 space. This is one of the 5 symmetries. I'll mention another of the sort of symmetries that comes up in this slide or two. Okay, so strongly invertible knots, at least we know what it is. And the rest, I'll say something about in the next slides. So the plan for the talk is, okay, I'll explain what the main theorem is. Actually, the sort of excuse for talking about it is going to come slightly later. Then I'll remind you what Khovanov homology is. I'm actually going to do that in 2 different ways. I'll tell you what Khovanov homology is combinatorially, the classical definition, and then I'll explain conjecturally how it arises in symplectic geometry. So what the symplectic construction is believed to be. And then we have the theorem and the ingredients. So I'll give a little application just to illustrate that the main theorem isn't vacuous, has some content. So an application to sort of 3.5 dimensional topology, and then talk a little bit about the sketch of the proof, just a slide or two, and talk about some related results that are more directly connected to symplectic geometry. And again, feel free to interrupt if you have questions. So as I said, the talk is going to be handwritten in my wonderful penmanship. So the main theorem is theorem with Sucharit Sarkar, given a strongly invertible knot K, in S3 with quotient K bar, there's a spectral sequence from the Khovanov homology of K with coefficients in F2 to a version of the Khovanov homology of the quotient. And now, really, to get the spectral sequence to be graded in the way that you expect spectral sequences to be, there's some blow up by the Laurent polynomials hypothesis. So again, there are several things in the statement that I should explain. I briefly said it, but I would say a little bit more about strongly invertible knots. I should tell you what the quotient of a strongly invertible knot is, and then I should explain what this Khovanov homology thing is. So I'll do the first two on this slide and the next one on the next slide. So strongly invertible knot, here's a example. So here's a knot. This is just the trefoil. And there's an axis. Here's the axis, which intersects the knot in 2 points. So that rotation by pi around this axis takes the knot to itself. So given that, there's a quotient knot, which is, well, which I'll draw. So the quotient by the symmetry, well, actually the quotient by the symmetry is really a tangle, because it's sort of got these sort of, you end up with these 2 endpoints when you quotient by, and then that's connected by, so a piece of the quotient is built here from the piece of axis there. So it's built from the quotient of the knot union a part of the axis. There's another way to draw these knots, which is going to be actually more relevant to the main theorem. So in the picture I just drew, the axis is in the plane, but you can also draw it with the axis perpendicular to the plane. So let me show you what I mean, hopefully. So there's the same knot, hopefully, the trefoil again. But now if you think about the axis as a vertical line coming out of the page where I put this dot, so the action now is rotation by pi in the page around the axis, then that's another view of the same knot. So there have been these strongly invertible knots have come up a fair amount recently, so there are now words attached to these. I think the name's due to Keegan-Boyle. This is kind of diagram is called transvergent. The movement is transverse to the plane, whereas here it's intravergent. The movement is in the plane. And here you can see the quotient again, maybe more easily. So you take the knot, and now if I resolve, there's one crossing on the axis. So if I resolve that on-axis crossing, there are 2 ways I could do that. I could resolve it like this, or I could resolve it like that. And the axis is still there. Then I have a symmetry of the knot, which is disjoint from the axis. So these still have a rotational symmetry by pi around the dot. With no fixed points. I'll give you a word for that in a second. Or sorry, no fixed points on the knot. And then you can take the quotient. So the quotient by the action looks like that in both cases. Though where the axis is in the quotient is different in the 2 cases. So this kind of symmetry where you have a rotation by around an axis that's disjoint from the knot, this also has a name. These are called periodic knots. 2 periodics, it's a 2-fold symmetry. Okay, and these are the quotients. And again, the quotients really sit inside S3 minus the z-axis. so it's sort of thickened up annulus. Okay, and I'll just to announce, I'll explain it more later, but the sort of toy application I'm going to give for the theorem is that a particular knot, 946, has no equivariant slice disk. So I'll say a little bit more about that in a couple of slides. But the sort of studying surfaces with boundaries, these boundary strongly invertible knots, has been an interesting topic recently, and this theorem has something to say about it. Okay. So again, reminder that if you want to go backwards in the slides, the PDF's available of approximately what I'm writing online. That said, I'm going to flip. Oh yeah, so here's another example of some slightly more complicated knots. This is, I think, actually 946. So the knot I announced on the previous slide. And so this is also 946. This introversion diagram turns out to often be more complicated, sometimes more complicated than the transvergent one. So here again, the symmetry is rotation by pi around its axis, or in this case, it's rotation by pi around the axis perpendicular plane there, so by pi in the plane. What's happened in the middle picture is I've taken the knot and I've resolved it along the axis. So I've made it disjoint from the axis by attaching a band there. So that's this. And it's not important for this talk, but I chose the band so that the linking number of the two components is 0. It's by putting a little couple of on-axis crossings there. So this is K. This is a sort of resolution of K. And this is the quotient. Once it doesn't intersect the axis anymore, here's the axis there. Once it doesn't intersect the axis anymore, it's easy to take the quotient, see that you have a knot in S3. And here's the introvergent picture for the same knot. So you have this knot, resolving it along the axis gives you, well, there are two different ways to do it. Resolve that crossing, again, once you do that, you have either a knot there or a link there. And you can take the quotient, and you get, doesn't matter which way you resolve it in terms of taking the quotient, except that where the axis is slightly different. Okay. Khovanov homology. So
Robert, two quick questions before you move.
Please. Yeah.
Sorry, actually, maybe this slide and previous one. By periodic knots, it really doesn't refer anything about not being fibrate and related to monodromy of such a knot, right?
That's right. That's right. So you might think another reasonable definition of periodic knot would be a fibrate knot where the monodromy is a periodic diffeomorphism, but it's totally unrelated. So,
and the other question is for your toy application. So you really want to stick with the 946? Like, for example, is mirror, is the answer similar?
I guess if the mirror had equivariant slice disks, then you could just mirror those disks and that disk, and you would get an equivariant slice disk for 946. So it's the proof. You could turn around the proof to do it directly for the mirror using Khovanov homology, though you're right that, of course, you're right that often these sorts of invariants are very sensitive to orientation, so it can matter. I'm not going to do it on the slides, but you could write some conditions on the invariance of a knot that would imply that this strategy works for the knot. You need sort of fairly simple Khovanov homology, and then the strategy I'm going to give will apply. But I don't have any other examples in my pocket other than 946, so that's a little sad.
Okay, that's okay. Thank you.
Yeah. No, thanks. Any other questions from anybody? Okay, so thanks to everybody for continuing to put up with this low-dimensional topology stuff. There'll be, I promise, not this slide, but the next slide will at least have some assertions about symplectic geometry. But before I do that, let me just tell you what Khovanov homology is. So by the end of this slide, if you don't already know what Khovanov homology is, you'll know how to write it down and compute it, what the construction is. So we start with a knot inside S3. And formally, what Khovanov homology is a bigraded abelian group. KHIJ of K. And I've given an example over here on the right for S3, sorry, not for S3, for the trefoil. So 3,1 is the trefoil, the knot that I keep drawing more or less. And so bigraded abelian group means that for each pair of integers I and j, you get a abelian group. It's finitely generated, so there are only finitely many places non-zero. So for example, for I equals 0 and j equals 1, it's z. For I equals 2 and j equals 7, it's z equals 2. It tends to be sort of concentrated near this diagonal where I minus 2j is, j minus 2i is constant. So this is a not particularly deceptive picture of what these kinds of things look like. Though, of course, if you don't take the simplest knot, they get a little bit larger. This group is the homology of a chain complex. That's why it's called Khovanov homology. Well, it's why it's called homology. It's discovered by Khovanov, which I'll call CKHIJ of K. The differential preserves J and say decreases I by 1. And I'll construct it. So the construction is combinatorial starting from a knot diagram. So let's take my favorite knot diagram, which is a diagram for the unknot. So here's K. Now, K has various crossings, and if you turn your head or straighten things out, you can make each crossing look like the crossing I just drew. And so when you resolve it, there are two ways you can resolve that crossing. There's a 0 resolution like that and a 1 resolution like that. If you walk along the top strand and turn left, so to resolve, you get the 0 resolution, or if you walk along the top strand and turn right to resolve, you get the 1 resolution. So I can do that at all of the crossings of K, and that gives me 2 to the n different complete resolutions. In this case, that's 4. So if I do the 0 resolution at both of them, so here's the 0 resolution. I walk along the top strand and turn left, walk along the top strand and turn left, or I could do the 1 resolution at the second one and the 0 at the first. So same resolution that I had there, but the 1 resolution there. Or I could do the 1 resolution at the first and the 0 at the second, or the 1 resolution at the first and the 0 and the 1 resolution at the second. You get a little cube. For every edge in the cube, either 2 circles are merging or 1 circle is splitting apart. Each edge corresponds to a saddle cobordism. Okay, so that's ingredient 1 in the construction. Ingredient 2 is a particular ring. It's the ring Z adjoint X mod X squared. So that's it's a ring, so it has a multiplication from V tensor V to V. It's just multiplication of the ring. It also has a co-multiplication. That's a map from V to V tensor V, given by the coproduct of 1 is 1 tensor X plus X tensor 1, and the coproduct of X is X tensor X. Now, to get the Khovanov complex, what you do is you take each circle in this cube of resolution, then you place it by a copy of V, and disjoint union by tensor product. So for the cube of resolutions I drew, here's V tensor V tensor V, V tensor V, V, and V tensor V. And now, as I said, between any pair of adjacent resolutions, either two circles are merging or one circle is splitting apart. And so if two circles are merging, you multiply, and if a circle is splitting apart, you co-multiply. For this vertical edge, nothing is happening in the first circle, but the last two are multiplying. So you do the identity tensor M multiplication. And for this one, the first circle is splitting apart and the second circle is doing nothing. So this is co-product composite identity. It turned out that this cube commutes. That's because V is what's called a Frobenius algebra. And then you can put in some sign to make it anti-commute. Maybe I'll put in a minus sign there. And then you just collapse it to get a chain complex. So you take the total complex. That is, means I'm going to take the direct sum over diagonals. So take direct sums along these diagonals. So it gives me V tensor V, V tensor V, sorry, V plus V tensor V tensor V, and V tensor V. And the maps are just the direct sums of the maps that you had. So co-product on the first factor and id tensor multiplication on the second, sorry, first summand, that on the second summand, or in this case, minus multiplication and co-multiplication tensor identity. So this is the Khovanov chain complex. I didn't tell you the bigradings, but the bigradings are also fairly simple, and taking its homology gives you Khovanov homology. So it's a sort of simple combinatorial construction from a knot. And it looks a little bit, if you've seen the Jones polynomial and construction of that in terms of resolutions, this looks, this is Kaufman bracket, this looks similar. Okay. So again, one's supposed to get a bigraded abelian group associated to a knot. I thought I would spend just a slide describing the sort of symplectic and conjectural symplectic interpretation. Conjectural symplectic interpretation. Which was originally introduced by Paul Seidel and Ivan Smith in 2004-ish. And then the version I'm going to say is a little reformulation due to Lidman-Manolescu. And then the best connection we have to Khovanov homology at the moment is due to Mohammed Abuzaid and Ivan Smith. So, okay, I start with a particular, I'm going to build a particular symplectic manifold, in fact, algebraic variety. Smooth algebraic variety, start with C and fix a bunch of points in C. So I'll just take 0, 1, up to 2n. And the example that I'm about to draw below is going to be the case n equals 2. So I'm going to have an n equals 2 example that shows up in a sec. There's a unique monic polynomial which has zeros at these points. It's not particularly hard to write down. Z minus 2n. And from that, there's a three-dimensional complex surface. Sorry, not three-dimensional, two-dimensional complex surface. U squared, V squared, P of Z equals 0. Let's move that inside C3. That comes with a Lipshitz vibration to C just by taking the Z coordinate. So it has singular fibers over the point 0, 1, up to 2n. So the fiber over 0, it looks like a cone. So this is over 0, say, or over 2, sorry, 1, etc. And the generic fiber is a quadric. Okay. Now there needs to be a knot in it, and a knot contributes some Lagrangian submanifolds. So I'll just draw a particular example. You can always represent a knot as a union of bridges. So again, I'm doing something for n equals 2. And so here's a couple of arcs there, and let's see, that, that, and there, there. So this is the trefoil again. And think of I drew breaks in the red line, so you can see that this is a knot, but I'm actually going to think of these as continuous arcs. Okay, so let's call these arcs something. Let's say this is maybe A1, the other, so A1 ended here, so this is A2, B1 and B2. And each of these gives us a sort of Lipshitz thimble or union of two Lipshitz thimbles. So gives me Lipshitz thimbles alpha 1, alpha 2 corresponding to A1 and A2, and beta 1 and beta 2 corresponding to B1 and B2, all sitting inside this surface S. So that's alpha 1 is a union of vanishing cycles along A1. Alpha 1 is a union of vanishing cycles along here. And now, if I take S times S, I can think of alpha 1 cross alpha 2 as sitting inside S cross S, and beta 1 cross beta 2 sitting inside S cross S. The construction I want is actually not exactly that. It's a sort of symmetric product or a resolution of symmetric product called the Hilbert scheme of points in S, actually a relative Hilbert scheme. So it's roughly this is like S cross S in general across many n copies of S mod an action of the symmetric group. Though it's not quite that. It's a blow up of that along some diagonals. Okay, and then symplectic Khovanov homology of our knot K is the Lagrange intersection Floer homology of this product of these Lagrangians, these products of two spheres. Oh yeah, these are all two spheres. S2s. Beta 1 cross beta 2 inside this Hilbert scheme. So results. So the first one was due to Seidel and Smith that this is a link invariant. This is not invariant. Doesn't depend on the particular bridges you chose. And they computed it for some examples, including the trefoil, and saw that it agreed with Khovanov homology in those cases. More recently, Abizayed and Smith showed that if you just compute the Khovanov homology over Q, this is in fact isomorphic. Sorry, it's going to be a great theorem. The Khovanov homology and the symplectic Khovanov homology over Q agree. So in characteristic 0, the two invariants are the same. So this actually did recover Khovanov homology. And an older, so that's that's from about 10 years ago. An older result of Seidel-Smith is that they observed that for two periodic knots, so again, that's having this symmetry along an axis disjoint from the knot, there's a spectral sequence from the Khovanov homology, a symplectic Khovanov homology. symplectic Khovanov homology of K, with coefficients in F2 to the symplectic Khovanov homology of its quotient. So this is quotient. And always there's this extra Laurent polynomial thing sitting around. Laurent series thing sitting around. Okay. Notice that these two theorems are sort of incompatible in the sense that the Abuside-Smith theorem is, in characteristic 0, whereas this result relating the knot and its quotient is in characteristic 2. So it's, I think, widely believed that this symplectic Khovanov homology is the same as Khovanov homology also, over Z, but nobody has any idea how to prove it. I mean, maybe it's widely believed, because if it isn't Khovanov homology, what on earth is it? Though the fact that nobody's proved it is maybe, a slightly alarming sign. Okay. I'll sort of sketch how the main theorem is powerful enough to actually say something about low-dimensional topology, just to convince you that there's some content to these kinds of results. And then we'll go back to, then after that, I'll say something about how the main theorem is proved and how something about some other connections to symplectic geometry. So, so again, what was our theorem? So the main theorem was that for K strongly invertible, the Khovanov homology, there's a spectral sequence from the Khovanov homology of K to some version of Khovanov homology of its quotient. Right, there are lots of things I'm happy to explain more at the end, like what is this AKH? Let's see if my picture's in the way. But it's just some variant of Khovanov homology. To use this, I need a little bit more than what I've told you. And I've suppressed this Laurent series here. I'll start doing that more systematically. The first differential in the spectral sequence is id plus tau star. Okay, what on earth is tau star? So tau is the symmetry, this Z2 action of K, the Z2 action S3 rotation. And that induces a map on Khovanov homology. Khovanov homology is natural in some sense. You could actually just see that from the description I gave, that if I had a symmetry, that gives you a symmetry of the cube of resolutions, and that gives you a symmetry of the chain complex. And the second property that I'm not going to write out fully is that the gradings of the differentials in the spectral sequence are predictable. I mean, they change the grading, but in a controlled way. Predictable. So from these properties, you can determine the action of the symmetry from knowing just the groups, the Khovanov homology of K and the annular Khovanov homology of the quotient. So you can, and the software, for example, compute the Khovanov homology of K and more or less compute the annular Khovanov homology. So you can compute the action without actually having to study the action on this complex. Okay, the second ingredient I need to get an application is a relation to cobordisms. Given a cobordism of knots, so that's a cobordism from, or links from one link to another. So that's a surface in 0, 1 cross S3. There's an induced map on Khovanov homology, map F lower star from the Khovanov homology of L0 to the Khovanov homology of L1. And okay, those maps could always be 0. That would be not very useful for anything, but there's a non-degeneracy result for those maps. So if that cobordism is actually a disk, then there's a non-triviality result. So this map F star is non-trivial. That comes from the thinking about the Lie deformation. Okay, so those are all the ingredients that are needed for the application. I didn't say any of them particularly precisely. So now, if you combine these and just a little bit of cleverness, then for the knot 946 or other knots with similar Khovanov homology, this gives that tau star circle F star is not F star for any slice disk. So I should say something about this slice disks. I'll do that. Any slice disk F for 946. First, maybe I should even tell you what a slice disk is. So slice disk for K is just a, is just a disk inside B4 with boundary of D equals K inside S3. 946, that's this knot in the bottom right, has a slice disk. If you take 946 and you attach a band along this red arc here, then the result is a two-component unlink. You can sort of see that if I attach a band, then it smooths out here, and then you can sort of untwist, so it's smooth out there, and you can untwist all those crossings, and everything else just sort of, you can then fold something through, and everything else falls apart. So I attach a band along there, I get a two-component unlink, and just fill those in with disks. That gives me a surface inside the 4-ball, not an S3 because the disks intersect the band I attached, but gives you a disk inside the 4-ball, and with boundary that knot. There's another one, I chose that arc, but there's an obvious symmetry. I mean, it's strongly invertible, so I could have chosen that one. Instead, it gives me a different slice disk. Both of these slice disks induce maps on Khovanov homology. In fact, any slice disk does, but none of those maps is preserved by this involution on the Khovanov complex induced by tau. 946 has no equivariant slice disk. Equivariant slice disk. Because if it did, the map associated with the equivariant one would have to be preserved by tau. I think the fact that 946 has no equivariant slice disk was probably known for a long time, though I don't know the original reference. Some people, I should point out, this sort of using Khovanov homology to study surfaces in force space successfully was first pioneered in a paper of Sundberg and Swan from about 5 years ago, not long ago. And using this sort of technique, not the spectral sequence, but studying actions on Heegard-Floer invariants, so related invariants, to rule out equivariant slice disks was done by Malek Stoffregen, again, a few years ago, and before we wrote our paper. So ours is using a similar technique to theirs in a slightly different context, plus a spectral sequence. This turns out, I'm not going to digress to talk about the low-dimensional topology, but this sort of studying equivariant surfaces turns out to be an interesting thing. So for example, there's a concordance group of strongly invertible knots, and that group turns out to be non-commutative, and there are a number of questions about its structure. So it's the first example of cobordism or concordance group that I'm aware of that actually has a naturally non-commutative group. And there are conjectures about it, like that it contains the free group on 2 generators. So it's actually really big. That's open. Okay. So doing fine for time. I have a little bit of time, so I'll tell you a little bit about the proof of the spectral sequence, so that the proof that the spectral sequence exists. I pre-wrote a little bit. So the proof actually goes back to classical work of not Ivan Smith, but P.A. Smith from the 1930s. So this is, I'm going to sort of tell you a little about Smith theory in the classical sense due to P.A. Smith, roughly 1934. At least that's the publication date of one of the key papers, publication year. So start with a CW complex X with a Z2 action. And here I mean a slightly strong sense. So if tau, that's my generator, Z2 is 1 tau. If tau takes a cell to itself, so it's supposed to act cellularly, take cells to cells, and if tau takes a cell to itself, then tau restricted to E is the identity. So as the Z2 action that's cellular in this sort of strong sense. Then there's a spectral sequence from the homology of X to the homology of the fixed set of the action. And here's how you prove that. This sort of the proof is at the level of exercises you could give in a beginning course on spectral sequences. So construct a bicomplex. Here's a bicomplex where the columns are just the cellular chain complexes, C0 cell, C1 cell, etc. The cellular chain complex of X. And the rows are given by identity plus tau. So tau is or tau sharp, the map on chain complexes induced by the symmetry. So now, and everything is with F2 coefficients. I haven't written the F2s everywhere, just for space, but everything's with F2 coefficients. So now, why is this a bicomplex? Well, if you take id plus tau squared, this is id plus 2 tau plus tau squared. 2 is 0, and tau squared is id, so that's 0. And because tau is a chain map, each of the squares, so you have a bicomplex. Bicomplex gives you 2 obvious spectral sequences. You can take homology vertically first or homology horizontally first. So if you take homology, homology vertically first, that is, you use the horizontal filtration to induce a spectral sequence. Then you get the E1 page is just H2, H1, H0, H2, H1, H0, etc. And the D1 differential will be id plus tau star. Id plus tau star. So this at the E1 page, you see these groups. The theta inverse is just the different columns. It's just translating horizontally. If you take homology horizontally first, what does id plus tau star do? So the kernel of id plus tau star is generated by 2 different kinds of things. It's generated by the fixed cells, because if tau of E is E, then id plus tau of E is 0, working on 2, and by cells of the form E plus tau of E, where E is not fixed. And the image is generated by these E plus tau of E's. So the E1 page is just given by the chain complexes of the fixed set. And you can see that it's easy to see the E1 differential. E1 differential is induced by boundary, so it's the differential in the cellular chain complex of the fixed set. And then because the chain complex of the fixed set is a subcomplex that followed from this condition, the spectral sequence collapses at E2. This one collapses at E2, which was the homology of the fixed set. So there you got the right-hand side. So because this spectral sequence converges to the homology of the fixed set, we made many copies of it. Then, oh, I see. Well, fine. Then the other spectral sequence also converges to the homology of the fixed set, but it started from the left-hand side. So that's the spectral sequence we want. Okay, so that was sort of classical Smith theory for CW complexes. Left on that cube in case it's useful. So then to apply this to Khovanov homology, well, fortunately, there's a result that the Khovanov homology of a knot, given a knot K, there's a CW complex, a sort of natural CW complex, X of K, such that the homology of X of K is the Khovanov homology of K up to a grading shift. And this is natural enough that for K strongly invertible, you can arrange that this X of K can have, so that has a Z2 action. So X of K is built in some similar way to Khovanov homology, and in particular inherits an action from the way you get one on the Khovanov complex. Then you can apply this theorem at the top, and it gives you a spectral sequence to something. And the main work is you need to identify what is the fixed set. So identify the fixed set, X of K fixed. And fortunately, how to do that was discovered in the two periodic case by other people. So the technique to identify the fixed set is due to Stoffregen-Zhang, who had studied this in the p-periodic case. And there's also a variant of that slightly later due to Borjic and Politsarchik. Okay, that's the hard part of the lecture, and Silvera. This construction, I guess, again, this is supposed to be symplectic geometry talk. This construction of CW complex coming from that gives you Khovanov homology was inspired by this program of constructing a Floer homotopy type, first proposed by Cohen, Jones, Siegel. And our construction uses a sort of topological part of their construction. So it's, again, input from ideas in symplectic geometry, though there's no actual symplectic geometry in the constructions on this page. Okay, so in the last few minutes, I thought I would say a little bit about related work. This question of studying the sort of localization results for symmetries for low-dimensional invariance has been sort of a popular topic. There's been a lot of interest in it. I was first interested in these things maybe in 2004, 2005, but I couldn't prove anything. But then, fortunately, lots of other people had lots of ideas for proving things since then. So as I mentioned, the first results of this forum were due to Seidel-Smith and were for symplectic Khovanov homology. In the case P equals 2, so the restriction there seems to be, well, has not been lifted. This is part of a general story I mention here. So decorate this a little bit. So there's a general story for Lagrangian intersection Floer homology under restrictive hypotheses, quite restrictive hypotheses, relating the Floer homology of a pair of Lagrangians and the Floer homology of the fixed sets. So that was a tool that they introduced and that they applied to Khovanov homology. As I said, for p-periodic knots, so again, p-periodic is like, here's a drop figure if it's going to help anybody. Here's a 3-periodic diagram for the trefoil. Means rotation by around an axis disjoint from the knot preserves the knot. So rotation by a third preserves the knot there. In the p-periodic case, I said there's a result of Stoffregen-Zhang and then reproved by this other group relating Khovanov homology and of the knot and the Khovanov homology, the quotient. So it's sort of similar to the first one, except that their E-infinity page is a little bit bigger, so it's a bit of a refinement, and they do it for any p. This comes from using the technique on the previous slide, this homotopy type. So this is via the homotopy type. There's also a related family invariance, Hegardt-Floer homology. And maybe I could have put in this, and so Princeton proved an analog for p-periodic knots for Hegardt-Floer homology, not Floer homology, that there's a spectral sequence from, relating the knot in this quotient. Again, this is in the case p equals 2, and that restriction comes to the fact that, again, the Seidel-Smith theorem is an input there. In the strongly invertible case, what I'm talking about, okay, there's the main result that I gave, which I didn't restate on the slide. You can also study the Hegardt-Floer homology of the branch double cover, and there's a spectral sequence there relating the Hegardt-Floer homology of the branch double cover of the knot and the quotient. Those are invariants closely related to Khovanov homology. And again, this sort of uses the symplectic techniques, the localization for Lagrangian intersection Floer homology, not the original Seidel-Smith theorem, which isn't strong enough, but a refinement of it due to Tim Large. To get the spectral sequence I talked about, you need a version of this annular Khovanov homology, whatever that is. So there's a construction of that from a couple years ago due to Chuck Umak and Ivan Smith. But that construction doesn't obviously tie into the construction that I get, the spectral sequence here. But then there's a new construction due to Kristen Hendricks, Chuck Umak, and Sriram Raghunath, who's a student of Kristen's. I hope I got the first name right. Yes, Kristen said I did. Good. So they give a new construction of analytic Khovanov homology is sort of more what you would expect the construction to look like, what I would have expected in my naive nature. And using that new construction, they are able to produce a symplectic version of a spectral sequence. Again, I guess the second half of that probably uses the Seidel-Smith or large localization theorem. And again, what to say about that? It doesn't follow from us. We don't know symplectic Khovanov homology is Khovanov homology. We definitely don't know that annular symplectic Khovanov is annular Khovanov homology. So, one can conjecture what the relation is, one doesn't know. Another thing you can do is study the knot Floer homology of the periodic knot. If only I had a strongly invertible knot. If only I had one sitting on the page. Okay, here's the strongly invertible knot. And it's natural to view that as a trivalent graph using sort of the half-axis, especially thinking about quotients. And so another student of Kristen's has studied the Hegardt-Floer homology there and proved a spectral sequence relating a Hegardt-Floer invariant of trivalent graphs, sort of for the knot union of the half-axis and the knot Floer homology of the quotient. So Harik, another student of Kristen's. Fine. There are a few instances of these sorts of spectral sequences purely in symplectic geometry. So I want to note two. Well, one is these ones for Lagrangian intersection Floer homology that are known, again, under some fairly restrictive hypotheses, though not as restrictive as they used to be because it's large. Using those, or a separate idea, Princeton and independently Paul Seidel gave a spectral sequence, or subsequently Paul Seidel gave a spectral sequence from the fixed point Floer homology of symplectomorphism phi, its square, and phi. So this is sort of, I mean, this is morally saying that phi squared has at least as many fixed points as phi. Though, of course, it's not really saying that. I mean, it's saying something that's obvious, but this is saying that some version of that statement that's preserved under Hamiltonian isotopy. I mean, it's the statement that's there. But sort of it's a Floer homology version of that obvious statement, but an extremely non-obvious Floer homology version. The other thing I want to say is that there was a strategy I was using on the, this shouldn't say spectral, this should say spectra. The strategy I was using on the previous page used the Khovanov stable homotopy type, and the technology has been developed in Tim Large's thesis and other places, and maybe will be written down in forthcoming work of Ivan, perhaps, that gives you a symplectic Khovanov stable homotopy type. Okay, fine. So that was sort of a key ingredient on the previous page. And again, there's a symplectic construction of that. And here, symplectic Khovanov homology is conjectured to be Khovanov homology, but I think the community really has no idea whether the symplectic Khovanov homotopy type is the same as the combinatorial one or not. So in the sense that, like, you know, I have some correspondence with Ivan where he's, you know, sort of speculating one way or the other. It's not clear at all. Okay, I thought I'd end with a couple of questions. One is that could maybe be attacked by symplectic geometers as an application to low-dimensional topology or these sorts of invariants. The other is sort of internal symplectic geometry. As I said, there are a few kinds of symmetries, of periodic symmetries of knots. Another one is there's an action of ZP on S3 with quotient lens space, LPQ. So there's a free action of ZP on S3. And you could look at knots that are preserved by that. Those are called freely periodic knots. And there are diagrams adapted to them, but not in a simple way that we used for Khovanov homology. So it'd be interesting to know if there's a relation between Khovanov homology of the knot and its quotient. There is sort of a sensible Khovanov homology for knots in lens spaces to some extent. And it seems hard to prove that from combinatorial Khovanov homology because that you really need diagrams that are preserved in order to run the strategy that I've said before. At least I don't know how to do it combinatorially, but maybe symplectic Khovanov homology is a little more flexible and will let you say something. So here's a place that symplectic Khovanov homology's flexibility and symplectic geometry strength might really get you somewhere farther. And then the second sort of meta question is, there's been a lot of interest in these sorts of localization questions in low-dimensional topology, these in low-dimensional Floer theories, but not so much in symplectic geometry. So just in general, do these sorts of ideas, localization ideas, have more purely symplectic applications? And I'm optimistic that they do, but I have some ideas, maybe what one might look at, but not really a clear idea of exactly what to do. Okay, so I think that's all I wanted to say. Thanks very much for listening.
Fantastic. Let's thank Robert for this wonderful talk.
Thanks.
Very nice. I think we have a few minutes for questions before I stop the recording. Any quick questions for Robert?